Hello and welcome to EC Electronics. So in this video we are going to see about the Nyquist Stability Criteria. We'll be seeing what is the Nyquist Stability Criteria and how is the basis, that is how is it connecting with the open loop and the closed loop transfer function. What is the difference of this criteria from the other criteria which we use for finding the stability of a system. And also we'll be discussing about the encirclements and the enclosements of the G of S, H of S plane, which is again a very important thing for finding the absolute stability. Okay, so we'll be discussing about the absolute stability and also the critical point also. Okay, so in this video, we'll be studying everything about the Nyquist stability criteria. So in this video, we are going to discuss about the Nyquist stability criterion. So we have in the previous videos, we have discussed about the root locus, its stability criterion, the Bode plot, its stability criterion. Just like that, for Nyquist plots also there is stability criterions, or generally there is a stability criterion called Nyquist stability criterion. Okay, so there is a different mode of approach of seeing the stability in this criteria. Let us see what is that in this video. Okay, so we'll be discussing about the basics and also we'll be discussing about the encirclements and the enclosements of the Nyquist plot, how it is related, all those things we'll cover. Okay, so if you don't know anything about Nyquist stability criterion, don't worry, we'll study on the flow. Okay, just watch the video to the end. Okay, so what we are doing in Nyquist stability criterion, let's start from the very basic. We are going to take the open loop transfer function. So the open loop transfer function, if you have seen my initial videos on the transfer function, open loop and closed loop, all those things, then you should be knowing the open loop transfer function TF, open loop TF. It is given by G of S, H of S. We generally write it in the Laplace domain. So it is G of S into H of S. Okay. So this is the open loop transfer function. So in Nyquist stability criterion, what we are doing is we are going to take the open loop transfer function, and by using this open loop transfer function, we are going to determine the stability of the closed loop system. Okay, so that is the basic thing that we are doing in the Nyquist stability criteria, and it is the difference of the Nyquist stability criteria from the other criteria. Okay, so we are going to take this G of S, H of S, and then we will be determining whether our closed loop system is stable or not. So we are not going to write the closed loop system's transfer function or anything. We only require this. Now how we can do it, let us see. Okay, so this is the basic thing. This is the thing we are going to do here. And also you should be knowing one more important thing, that while plotting the Nyquist plot, you are going to plot from minus infinity to infinity. Whereas in polar plots, you will be plotting only from 0 to infinity. So just for your information, I'm saying. Anyway, very soon we'll be doing a video on comparison between Nyquist and polar plots. So here, that is for Nyquist plots, we'll be drawing from minus infinity to infinity. Okay. Now, how can we find the closed loop system stability from the open loop? Let us see first. Okay. So, I'm going to remove all these things. Let us start from the very basic. Okay. So, I'm going to consider an open loop transfer function G of S, H of S as, I'm going to take a small one, S plus A by S into S plus B into 1. So, this is my G of S value and my H of S is this, and it is 1. Okay, so this is a indication that the feedback is a unity feedback. Okay, so here in bracket H of S is equal to 1. So, this is a unity feedback system, or you can simply write it as, you can ignore the 1. Okay. So this will be your G of S, H of S. Okay. Now consider that your system, that is your closed loop system, is having a negative feedback. The negative feedback is actually the desired feedback, or the desirable one. More negative feedback is actually desired. Why? Because it is more stable. Okay. So consider that your closed loop system is having a negative feedback. So how will you draw your system? If you have seen the previous videos, you should be knowing, or the initial videos, there will be a G of S and there is a feedback path which is having H of S. And it is connected to the negative unit of the summing, or the negative portion of the summing point. Okay. So this is negative. Okay. Your input is R of S. That is, input to the closed loop system is R of S. We'll use a different color. That's better. Okay. So the input to the closed loop system is R of S and the output is C of S. Okay. So this much will constitute your closed loop system. I'm just drawing it for your understanding. Okay. So G of S, H of S, it is nothing but the open loop transfer function. Okay. Now, first I'm going to find my closed loop transfer function. Okay. Just for, that is how it is related. How can we find the stability of the closed loop from the open loop? You need to first derive, right? So for that purpose, I'm going to take the C of S, R of S, or I'm going to find my closed loop transfer function. Okay. So I'm going to find my closed loop transfer function. TF means transfer function. Okay. So I'm going to find my closed loop transfer function now. So the closed loop transfer function will be the ratio of output to input. So this is entirely your closed loop. Output is C of S, input is R of S, which will give you, the ratio will give you your transfer function, right? So C of S by R of S, and its equation, since it's a negative feedback, it will be G of S by 1 plus G of S, H of S for a negative feedback. Okay. So this is your equation. In this, substitute this value. What is G of S? You know. H of S we know it is 1. So you can actually replace this equation with this much. Okay. Why? Because H of S, I'll write it here. H of S is equal to 1. Okay. So this will be your equation for the closed loop transfer function. In this, substitute the value of G of S. And you will be getting S plus A by S into S plus B totally by 1 plus S plus A by S into S plus B. Now there is a time for simplification. Simplifying, you will be getting S plus A by S into S plus B by, just cross multiply this term in the denominator. So you will be getting S into S plus B plus S plus A by S into S plus B. So in this term, you can cancel out this term in the numerator with this term in this denominator. And the resultant you'll be getting is like this. I'll write it here, S plus A by S into S plus B plus S plus A. So this will be your what? Closed loop transfer function. Okay. So you have obtained your open loop transfer function. The closed loop transfer function equation also you have obtained. Now, I'll write it here. Okay, take 1 plus G of S, H of S. Calculate the value of this term. 1 plus G of S, H of S. Okay, I'm going to calculate it. So, 1 plus G of S, H of S means here it is H of S is 1. So, H of S is equal to 1. Substitute it as 1. So, you'll be getting 1 plus G of S only. And the value is here. So, 1 plus S plus A by S into S plus B. Just cross multiply. Very soon you will get to know why I am doing all these things. Okay. So, S into S plus B. Yeah. S is here. S plus B plus S plus A by S into S plus B. Okay. So, in the board there are 3 terms. 1. Open loop transfer function, its simplified version, and closed loop transfer function, its simplified version. And also, thirdly, we have found 1 plus G of S, H of S, its simplified version also. Now, let us have a closer look in the 3 terms. Okay, let's have a look. So, this is the term 1, This is the term 2 and this is the term 3. Now, look at the numerator of the third term with the denominator of the second term. Are they equal? Yes, right. I'll write my inferences below. Okay. So, I'm going to use a different color. So, the numerator of 3 equal to, that is an equal, right? They are both equal. Numerator of 3 is equal to denominator of 2. Am I right? Yes. Okay. So, the numerator of 3 is the denominator of 2. That's right. Next one. Let us have a look at the denominator of 3. The denominator of 3 is equal to the denominator of 1. Okay. So, that is next inference. Denominator of 3 is equal to denominator of 1. So, these are my two inferences which I am getting after I write these three terms. Okay, so the numerator of 3 is equal to the denominator of 2 and the denominator of 3 is equal to the denominator of 1. So, how can you say the numerator of 3? So, the numerator of 3 means it is nothing but the zeros. We all know that if you equate the numerator term of a transfer function, you will get, if you solve for the s values, you will get nothing but zeros. Okay. So, the zeros of your third term. So, I am going to replace it with now the poles and zeros. Rather than just writing the numerator and denominator, I am going to write it in terms of poles and zeros. Okay. So, here if you are talking about numerator means it is zeros. Then if you are talking about denominator, numerator if you are talking about it is zeros. If you are talking about the denominator it is poles. Okay. So, rather than writing numerator and denominator, you can replace it with another terms. The numerator means zeros. Okay. So, the zeros of 3 is equal to the denominator of 2 means it is poles. Okay. I hope now it makes sense. So, this is the, if you solve for this numerator term, you will get zeros. And that zeros for the third term is equal to the denominator which is poles. That is, if you solve for the new denominator, you will get poles. So, the poles of second term. Okay. Now, we have rewritten the first inference. Again, same thing you can do for the second one which is denominator here. So, the poles of 3 is equal to again the poles of 1. Okay. So, here now you look at this two inferences. The zeros of the third term which is 1 plus g of s h of s is equal to the poles of the second term. What is the second term? It is a closed loop transfer function. So, you can say that the 1 plus g of s h of s term, its zeros are nothing but the poles of your closed loop transfer function. Okay. That is the denominator's roots. That is a poles. Okay. And also the poles of this third term, that is 1 plus g of s h of s term, is equal to the poles of your open loop transfer function. So, in order to find the poles of your open loop transfer function and the closed loop transfer function, you need not find the closed loop transfer function. You just have to take a term 1 plus g of s h of s. And if you take the 1 plus g of s h of s, its ratio you can actually say as the closed loop poles to the open loop poles. Okay. So, this is nothing but the closed loop poles. See here, poles of 2 means the closed loop poles. And this term is nothing but the poles of 1, which is nothing but the poles of open loop transfer function. So, from these two things, we can make an inference. Now, I am going to remove all these things from the board. Okay. I'm going to write my thing which I understood. That is, if you take 1 plus g of s h of s, okay, that is, if you take 1 plus g of s h of s, that is, just take 1 plus the open loop transfer function. For this term, the zeros are the poles of your closed loop transfer function, and the poles of this term, okay, we are talking about the zeros and poles of this term, that is 1 plus g of s h of s. So the zeros are constituting the poles of closed loop transfer function, and the poles are constituting the poles of open loop transfer function. Okay, so here we are getting that the zeros are constituting the poles of closed loop transfer function, and the poles are constituting to the poles of open loop transfer function. Okay, so in order to have stability, so here we actually need not find the closed loop transfer function. From this term itself, we will get the values of the poles of the closed loop transfer function. With the help of poles, we are actually defining stability, right? So for stability condition, all the zeros of this term are in the left half of the S-plane. So if the system has to be stable, that is, if the closed loop system or the closed loop transfer function has to be stable, then all zeros of 1 plus g of s h of s should lie in the left half of S-plane. Okay, so that is the stability condition. So all zeros of your 1 plus g of s h of s term should so it should lie in the left half of S-plane. Okay, so this is the stability condition. So for a system to be stable, you have to find the 1 plus g of s h of s term. Just remember that you are not taking your closed loop transfer function. You are only taking the term 1 plus open loop transfer function. And when you calculate it, the zeros of that 1 plus g of s h of s should lie in the left half of S-plane, because the zeros here are constituting the poles of the closed loop transfer function. So when you are saying the zeros here, these are nothing but the poles of closed loop transfer function. So we know that for finding the stability of a closed loop transfer function, we actually locate the poles of it, right? So the poles are actually now defined with the zeros of this term, that is 1 plus g of s h of s terms. Zeros is nothing but the poles of the closed loop transfer function. That is what we got from our previous inferences, right? So all zeros of this 1 plus g of s h of s, if they are lying on the left half of S-plane, means the system is stable. Otherwise, the system is unstable. So this is the Nyquist stability criteria. Now, if you go for an advanced version of it, that is, if you go for a more detailed version in terms of the encirclements on the g of s h of s plane and the enclosements, you will get a absolute stability definition. So next we are going to discuss about the absolute stability. For talking about absolute stability, before that, you should be knowing that there is a S-plane. So in this S-plane, we are going to actually mark the poles and zeros. That is, the S-plane, in this S-plane, we are going to mark the poles and zeros of our closed loop system. And based on the Nyquist stability criterion we have just discussed just before, I hope you understood that we are going to take only the term g of s h of s, which is your open loop transfer function. And by taking only the g of s h of s term, we are going to find whether the closed loop system is stable or not. Okay, so for this relation, we are going to draw a g of s h of s plane. So this is the g of s h of s plane, and this is the corresponding S plane of your system. Okay, so in this system, we are going to look for the poles and zeros. Based on the the diagrams or the encirclements, that is a name. Okay, so the encirclements of this this G of S, H of S plane, we are going to find how many poles are there, how many zeros are there, whether the system is stable or not. Okay, so we are going to look into this G of S, H of S plane, and this is the corresponding S plane. So after this point, we will be talking about a relation between S plane and G of S, H of S plane. All the criterias and everything will be saying in a connected way. Okay, so you should be knowing that for this S plane, we are actually marking the poles, and we'll be marking some encirclements and all in this G of S, H of S plane. And we'll look into this plane to find whether there is poles, or how many poles is there, or how many zeros is there, all those things. Okay, so here the stability, before saying the stability, there is one condition. Okay, so consider that based on this Nyquist stability criterion, consider that if there are P poles and Z zeros enclosed in the S plane, consider that there is P poles and Z zeros for the system. Okay, and it is drawn in this S plane. Okay, so if there is P poles and Z zeros, then the corresponding G of S, H of S plane will have N is equal to P minus Z encirclements. For your better understanding, so as I said, there are two planes, S plane is there and also G of S, H of S plane is there, and the relation between them, why we are taking is because in Nyquist stability criterion, we are only going to consider the term called 1 plus G of S, H of S, and with this term, we are going to find whether this given closed loop system is stable or not. Okay, so that's why there is a relation between the S plane and a G of S, H of S plane. Okay, so consider that I'm going to explain with the help of a small example here. So there is a S plane, and here the number of zeros is 3, number of poles is 6. Okay, so here the N equal to P minus Z will be 6 minus 3, and it will be 3, right? So there will be 3 encirclements actually. So if you look for this system's corresponding G of S, H of S plane, it will have N equal to P minus Z encirclements. That is, how many encirclements will be there? There will be 3 encirclements. See here, 1, 2, and totally 3 encirclements will be there. And also, so this S plane is having an enclosed region, means the region which is having your poles and zeros. Okay, so that region we called as an enclosed region, and this is the encirclements. Okay, so this enclosed region's direction, that is, if you see a blue colored region here, there is a direction for this region, right? So since the poles is more, the direction of your encirclements will be opposite to the direction of this enclosed region. So this enclosed region is pointing in this way, but your encirclements will be in the opposite way. Okay, so that is a relation. If poles is more, means there will be actually an anti-clockwise encirclements. If the zeros is more, means there will be clockwise encirclement, or the direction of encirclement will be closed, or that is clockwise. Okay, so we will discuss more about these while discussing the criteria. So next we are going to discuss about the criteria. So also, why I am taking negative, because since the direction is in the opposite way, that is in the anti-clockwise direction, there is a negative. Okay, so that is an indication of negative. So that is all about the thing. There is a connection between the S plane and the G of S, H of S plane. There will be an enclosed region, and for this enclosed region, we are going to mark some encirclements in G of S, H of S plane, and the direction of encirclements will be determining that whether poles is more or zeros is more. From that, we'll be determining the direction of encirclements, and how many encirclements is given by the equation N equal to P minus Z. Okay. So next we are going to see the conditions when poles are more, or only poles is present, or only zeros is present, how the encirclements will look like in the G of S, H of S plane. We are going to see. So next let us discuss the various conditions for encirclements in G of S, H of S plane. Okay. So the first condition is if enclosed S plane closed path. We have already seen how a S plane closed path will look like. That is an enclosed S plane closed path, how it look like, we have already seen. Okay, so if that plane or that path or that enclosement consists of only poles, then direction of encirclement in G of S, H of S plane is opposite to the direction of enclosed path. This thing actually we have discussed, right? So if this is the enclosed path. If it is direction is like this, then the direction in the corresponding g of s h of s plane, there is a direction of encirclement in g of s h of s plane will be opposite. Okay, so this thing we have already discussed. Okay, so this encirclement, which is in anti-clockwise direction. So generally the anti-clockwise encirclements are indicating only poles. Okay, so this is an anti-clockwise encirclement in g of s h of s plane, and it is indicating only poles. And the value will be n equal to -1. If there is only one pole, the value will be -1, minus because it is the anti-clockwise. Now, if there is only zeros, just like that, there is a statement here, but I have not written it. Okay, I'll say it for you. So if the enclosed S-plane closed path has only zeros for this case, then the direction of encirclement in G of S, H of S plane is same as direction of enclosed path in S-plane. So when there is only zeros for a particular S-plane enclosement, then the direction of encirclement will be this direction, that is clockwise. And it will be in the same direction of the enclosement in S-plane. Okay, and the value will be positive. Okay, now consider that there is a case for like this. There is one point here and one point here. Here, if you take the value inside this inner encirclement, the value will be 0. Why? Because there is one encirclement in anti-clockwise direction, one in clockwise. So it will get nullified and the value of n will be 0. But here if you take, the value of n will be positive 1. Why? Because it is outside of this inner encirclement. So here for this point the value will be positive 1. For this point the value will be 0. Okay, so generally if there is only poles, then there will be anti-clockwise encirclements. All the encirclements will be anti-clockwise. If there is only zeros, means all encirclements will be clockwise. Okay, next we are going to see about the critical point and the definition of absolute stability. So next we are going to talk about the critical point in absolute stability definition. So the critical point is the point -1 plus 0j is called the critical point, and based on this critical point, how can you define absolute stability? That is, if the point -1 plus 0j is lying outside the encirclement, then the corresponding closed loop system is absolutely stable. Okay, so this point should lie outside the encirclement. So in this video, we have discussed about the Nyquist stability criteria. We have discussed from the basics to all the details we have covered in this video. That is, we have also defined what is absolute stability, what is critical point, what are the encirclements and the relation between S plane and corresponding G of S, H of S plane. All these things we have discussed. Okay, so this is Nyquist stability criteria. I'm really hoping that you understood the topic. If yes, please do give it a thumbs up and also share it with your friends. And if you want more videos, please do subscribe to the channel. Thanks for watching and keep on watching.